Okay, thank you, Matteo. As already Matteo told, Volker is a full professor at Technical University of Berlin since 2000, and he has been a full professor at Technical University of Chemnitz in years 1993-2000. Now he's serving as president of the European Mathematical Society since 2019. And he has been president of the International Association of Applied Mathematics and Mechanics, GAMMA, in years 2011-2013, and chair of the Excellence Center of Matheon in Berlin, 2008-2016. He also served the mathematical community in many editorial positions. He's editor-in-chief of Linear Algebra and its Applications, and he has been a founding editor-in-chief of the Electronic Journal of Linear Algebra. Volker has been awarded of prestigious prizes, among which the SIAM WT and the Idalia Reid Prize, and the Hans Schneider Prize in Linear Algebra. Concerning his scientific activity, Volker has contributed to a large variety of topics in matrix theory, numerical linear algebra, theory and numerical simulation of differential algebraic equations, with applications in several areas of engineering, especially in systems and control theory, as well as in vibrational analysis. In the recent years, his research interests have been focusing on the study of systems having port-Hamiltonian structure, with applications to the modeling and simulation of energy transportation networks. And this is going to be the topic of his talk that is titled Energy-Based Modeling, Simulation and Control, Mathematical Theory and Algorithms for the Solution of Real-World Problems. Before leaving the script to Volker, if attendees have questions during the talk, they can write in the chat, and at the end of the talk, Volker will answer the questions. Thank you.
Yeah, thank you very much for the very nice introduction. It's a great pleasure to be, unfortunately, only virtually in Pisa. And so if you have an urgent question, you can also unmute yourself and just ask the question directly. So, as Beatrice mentioned, in the recent years, I have been very much interested in energy-based modeling. And this is what I'm going to talk about today. So, let me first start with the motivation. Oops. That I didn't want to do. So, as you all know, the climate change is really having a major impact on society. And so in Germany, the government has decided some years ago to move out of nuclear energy, and recently also to go out of burning coal. So the target ratio of sustainable energy that we plan to have by 2050 is something like 70 or 75%. And actually, the government has just recently made the numbers that we want this earlier. This is a very nice and good idea, but there is a problem with it, that the energy production, when you go to renewable energy, is pretty volatile. So, for example, here is a picture from 2018, and you can see the different types of energy sources and how much they contribute to the daily production. And as you can see, you have to switch between the different energy resources. So what are the challenges? First of all, we want our energy to come. So we want to run our computers, and so the security of energy supply has to be guaranteed. And energy conversion from one resource to another has to be efficient. And more and more we have to couple different energy sectors: wind, solar, gas, etc. Unfortunately, different components of energy networks have very different modeling accuracy, and different energy sectors also live on very different timescale. And due to the volatility, we have to deal with increased randomness and also with decentralization. So many households now have a solar collector on the roof, and local wind farms are everywhere and things like that. So the production is not done in a centralized way. So in order to deal with this, we need dynamical rather than stationary approaches. And the new buzzword that comes along with this is to build a digital twin that deals with these challenges in mathematical simulation, optimization, and in control, and in particular in real time. So what is a digital twin? There are many definitions. So for me, it's a network or a hierarchy or a catalog of dynamical system models of a real physical system consisting of mathematical equations with input, states and outputs, and parameters. And this kind of system is used for simulation, optimization, process control, prediction. And there are also, and we'll talk about this much more than about the classical physical models, data-driven models that incorporate measurements of parameters, sensor data. They monitor and incorporate information about the current state of the real system. So if you want to build such a digital twin, what you need is a system and network theoretic approach, like it has been done in circuit simulation already for the last 60 years. You need automatic software generation. That means modeling languages. And as I will tell you, you need energy-based models. For every component of such a model, you should have a whole hierarchy from very fine for the simulation to reduce order for optimization and control. And you should be adaptive in space, time, and model. You should be able to quantify the uncertainties. We should have sharing of computing resources, local and cloud computing, and the model should be evolved. And since 2020, we have a new big research lab in Berlin, together with the Siemens company, which deals with digital twins of several such technical systems. Today, because that's where we've done most of the mathematics, I will tell you a little bit about gas transport networks. So the last 8 years, we have a collaborative research center together with universities in Erlangen, Darmstadt, Duisburg, and the other two Berlin universities, and also with a company, Open Grid Europe. So if you want to study how gas flows in a pipeline network, you need a network of partial differential equations, and you have constraints. The equations are typically 1D Euler equations, or as will come in the future, when you mix hydrogen into the gas networks, we also have to include 3D models. We also have to incorporate temperature to describe the flow in the pipes. So the network model will include the flow balance and the network elements, which are sources, pipes, valves, compressors, and the consumers. So a very small typical network would look something like this: 2 compressor stations, sources S1 and S2, and consumers C0, C4, C2, and the C1 is over here. And there are also pipes between each of these components. So what are the components apart from these? if you look, this is a picture of a compressor station on the Czech-German border, and this is a huge factory which brings the pressure in the pipe up to a certain level, and this is really nothing you can model in detail. So typically you would have a curve like this, and the whole thing is a big control system which is based on surrogate or reduced order models. So whenever we have a compressor station here, this is really a data-based model that is incorporated here. And then we have a network. So these are the major lines in Germany, mainly coming from the Norway, from the Netherlands, and from Russia or Turkey. And then the network is split further and further and further and further. And so you can see this is a huge, complicated network to describe this. And essentially every household is one node in such a network. And now we look at the mathematical models. So for the flow in the pipes, we use compressible 1D Euler equations, which consist of three equations: mass conservation. So d rho dt is the x-axis is the space variable, t is the time variable, rho is the density times the velocity. So it's conservation of mass. Then we have a momentum balance here, where we have rho v again. Then we have the pressure and rho v squared. And then we have lambda divided by 2d. Lambda is the friction coefficient, and 2d is the diameter of the pipe. And it's again nonlinear here. And we also have a term which comes from the gravitational force. So g is the gravitational constant, and h is the height of the pipe. So that's the momentum balance. And then we have an energy balance. E is internal energy, and we have that the change of the rho times 1/2 v squared plus the internal energy plus this term here related to the change in space, plus a temperature term here comes in, where T is the real temperature, Tw is the wall temperature, and Kw is the heat transfer coefficient. So this is a set of partial differential equations. You have to add initial and boundary conditions to this. And just now think about the network I've just showed you. And now you have a PDE of this type on each of the nodes. You will get into mathematical challenges to solve this, and in particular, if you want to solve it in real time. So what people have been doing is they have been simplifying the model. So on top, we have the Euler equations with temperature. Then you could say, okay, I'm not in Russia, but I'm in Italy, and the temperature is pretty much constant. So I can look at the isothermal Euler equations. Or I could say gas flows with the speed of a bike. So maybe these terms are very small compared to the speed of sound. So I can drop these terms in the equation and I get a set of nonlinear equations. I could also say that rho times the velocity, the time derivative is small. Then I can go to simplified nonlinear equations, or I could say I'd look at the stationary model. I could also take the z component to be constant. Then I get an algebraic model where I can write down an explicit solution. And you can also do this in the isothermal case. And actually, the optimizers which optimize such a network, they even use a linear interpolation of this model here for the description. And if you're more interested, there is a pretty soon also in English a whole description of the hierarchy with all the components in the model hierarchy. The second application that I would like to talk about is district heating. So this is a project that we're having together with University of Trier, the Fraunhofer in Kaiserslautern, and the city works of Ludwigshafen. And there is the question, how do you model the district heating? So here somewhere is a heating plant. It pumps hot water into the pipes. These are the households. They take out the hot water and heat their house, and then they send the cold water back to the station. And so typically in Germany, we send it in with 84 Celsius and it comes back with 60 Celsius. So this model can be also described, and the equations look pretty much the same, except that now we have water, and that means we have to look at incompressible Euler equations, and so we have to add the incompressibility conditions. Other than that, it's a very similar model, and there is a description of the model in great detail in this paper, and I've given the slides to Paula so that she can distribute them if you're interested. Okay, so suppose we want to build a digital twin for one of these two networks. How do we do this? So let's say we make a wish list. What do we want? From physics and engineering, we want a representation so that coupling of models works across different scales and physical domains: power, heating, water, electricity, mechanical systems, thermodynamics. We want a representation that is close to the real physics, and that should work for open and closed systems. Open meaning I can put energy into the system and take it out, and closed systems like in classical physics modeling where you don't consider the interaction with the environment. It should be good for numerics, so the model class should allow for an easy discretization in space and time and model reduction. I will talk about this a little bit later. The class should be good for simulation, control, and optimization. Then it should have nice algebraic, geometric, analytical properties. We should be able to analyze it mathematically: existence, uniqueness, robustness, stability, uncertainty, errors. And since I'm coming out of the linear algebra community, I would like to have normal forms or linearizations. And in English, such a model that would fulfill all this would be called a jack of all trades. In German, it's called an eierlegende Wollmilchsau. It's an egg-laying wool milk sow. It's a perfect animal. So this would be what we want. And as you can imagine, we have to make a compromise but a model class that that comes very close to this thing is this energy-based network modeling. So the idea is you use energy as a quantity to communicate between different parts of the networks. So you look at energy transfer through inputs and outputs. You split everything into energy storage elements, energy dissipation elements, control inputs and control outputs, as well as interconnection, and you combine it with the so-called Dirac structure, and I will come back to that. And we would also like to have that every submodel is really a model hierarchy of fine or coarse, continuous or discretized, full or reduced or surrogate model. And the system theoretic way to realize such a energy-based network model is that of dissipative port-Hamiltonian systems, which operates via bond graphs. And there's a very nice open source book on the description on how to do this by Ian van der Schaft and Diederik Jelsemer. So what is a port-Hamiltonian system? A port-Hamiltonian system is, in its simplest form, it's a ODE, or it could be operator ODE system. X dot equals J, which could depend on time and space, minus R. And J describes the energy flux among energy storage elements. J is skew symmetric or skew Hermitian in the complex case. And R R describes energy dissipation or loss. Also, R is typically semi-definite matrix. And then we have inputs, B minus P times U, and outputs, B plus P times. And then there's here the gradient of an energy function, which is typically called Hamiltonian, and that's why they're called port-Hamiltonian system. Port for, because you have ports, output and input and output, and we have a Hamiltonian structure, and you have dissipation because you have this R. So I've written it in a more general form here. So the way to, we have also a feed-through term here, direct feed-through from the input to the output. And we require that J is skew symmetric, that the feed-through term is split into symmetric and skew symmetric part. And we require that this matrix W of T of X is symmetric or Hermitian and semi-definite. So it's R, the dissipation term, that's the P, that P here, and the S here together is positive semi-definite. And in the infinite dimensional case, these coefficients can be operators that map into appropriate function spaces. But in this talk, I will mainly stay, there's just a small part which goes to the Pde setting. So why should this be a good approach? So first of all, port-Hamiltonian systems generalize Hamiltonian systems. That means classical mechanics and electrical engineering is in there. They also generalize gradient flow systems, so that means thermodynamics is included. You don't have conservation of energy, but what you have is that this energy function H has the property that H at time t1 minus H of time t0 is bounded from above by the integral of the inner product of the output and the input. So this is a type of connection energy. That's the energy that comes in or out of the network. And so this energy function is bounded from above by what comes in and goes out of the system. That's what conservation of energy is replaced by. So if Y or U is equal to 0, then, and you don't have, and this matrix W is equal to 0, then you have conservation of energy. So the really nice thing for modeling is that if you take two pH systems and you connect them via in a power conserving way, then it's again a port-Hamiltonian system. So that means you can do modularized network-based modeling. Typically, port-Hamiltonian systems are stable and passive. H is a Lyapunov function. So if it's quadratic and if it's cubic or so, that may be different, then it's only local. And passive means they don't generate energy by itself, they only dissipate energy. And the port-Hamiltonian structure allows to preserve the physical properties in Galerkin projections, so Pde discretization and model reduction. And on top of this, they have wonderful mathematical structures. They have a very nice algebraic structure in the coefficients, symmetry, skew symmetry, semi-definiteness, and a geometric structure associated with the flow. But that would not be enough to describe our networks. So we need to add algebraic constraints like Kirchhoff's laws or position constraints. And together with my PhD student Ricardo Morandin, who some of you may know from Pisa, we created the following generalization of these systems to differential algebraic systems. And so I marked in red what has changed. So first of all, we can have a matrix in front of the x dot, so that matrix can be singular, so that if that has a kernel, then in that kernel we don't have a differential equation, but just an algebraic equation. Then we have a term R here, we'll say in a minute, and we have a term Z here that replaces the gradient of the Hamiltonian. Otherwise, the system looks exactly the same. And this system is called a port-Hamiltonian DAE if we have, again, the semi-definiteness condition of W. We have skew symmetry, not only by J, but also the remaining part is trivial. But then we have the relation between the Hamiltonian and these extra variables. So the derivative with respect to the state of the Hamiltonian is given by E transpose times Z, or this could be E adjoint if you have an operator. So this Z is related to the Hamiltonian. So if E would be the identity matrix, then this would just be, this Z would be just the gradient of the Hamiltonian. And the time derivative of the Hamiltonian is given by Z transpose times this R. And this R is needed to allow time varying changes of variables. So this looks pretty complicated at first sight, but we have exactly the same dissipation inequality. We have the power balance equation. So the total derivative of the Hamiltonian is given by this inner product of the joint variable Z and U with W in the inner product plus the inner product between Y and U. And that should hold for any solution and any input. And so if W is 0, then the total change in time of the Hamiltonian is just given by the Y and U. And if this is also 0, then we have the Hamiltonian character still. And we have the dissipation inequality. So that's nice. Further properties, if you take two such systems, you can make them autonomous. This structure is invariant under making the system autonomous. You just introduce T dot equals 1 as a new variable. And if you take two autonomous systems and you couple them in a linear combination, the inputs and the outputs of both systems, then the resulting system is again port-Hamiltonian, and the energy function is just added between the two parts. Again, it's invariant under nonlinear state transformations in space and time, and it's invariant under Galerkin projection. So all the properties pull over to the more general case. Just a quick word about what a Dirac structure is. I mentioned this is an interconnection structure. So let F be a linear space and E be its dual space. Then you define a bilinear form on F Cartesian product with E in such a funny way. You multiply F1 with E2 and E1 with F2, and you add the two. And this is the usual dual, the one bracket is the usual duality pairing. And the Dirac structure of such a pair of spaces is then a linear subspace that is equal to its orthogonal complement. So that sounds pretty awkward, but think about just a skew-symmetric matrix and the matrix 0, identity minus identity 0 would be typically a matrix that describes such a Dirac structure. And the elements of F and E are called the flow and the effort. And this can be done also in the nonlinear case. We are tangent and cotangent bundles. I will skip this here. Okay, so this is the class of problems that we're going to look at. And these could be, again, operators. And now the first thing is we look at time discretization. So if you discretize a differential algebraic equation, you need implicit or half-implicit methods to deal with the algebraic constraints. The port-Hamiltonian structure requires that the discrete time discrete methods satisfy the population balance equation and the dissipation inequality, at least up to the discretization era. And the discretization should essentially lead to a discrete time port-Hamiltonian system. And the methods of choice are partitioned Runge-Kutta methods and Gauss-Legendre collocation methods. And let me quickly tell you what the latter are. So what you do, you take an input u, you take an interval, split it into a grid, T0 to T1 with a grid size h, and you approximate the solution x of the differential algebraic equation by a piecewise polynomial of degree s that satisfies the port-Hamiltonian DAE in some collocation points in the interval, so T0 plus h times gamma I, where gamma I are between 0 and 1. And if Li are the i's Lagrange interpolation polynomial, so tau, product of tau minus gamma I divided by gamma I minus gamma j, then you get such a formula for an approximation of the derivative of the piecewise polynomials as an linear combination of the Lagrange interpolants. You require that at the collocation points at T0 plus T tau h, we write it in this way, and then we get that the xi is nothing else than x0 plus h times the sum of alpha ij times this xj dot. And the alpha ij are just the integrals over these Lagrange polynomials, and they are the Runge-Kutta coefficients, and the beta j's are the integrals between 0 and 1 of the Lagrange polynomials, and these are the Runge-Kutta coefficients to the method. And you can show that if you take such a method and you want to satisfy this Dirac structure property, which I skipped, then we can find exactly the conditions that the collocation for the flow part, for the dissipation part, and for the storage part, and the input and the outputs have to be satisfied in all the collocation points. And if you do that, then you can look at the Hamiltonian as a function of t. So you write it using the fundamental theorem of analysis. You write it as integral of T0 to T of h dot. And you get the power balance equation that the total derivative of this h function with respect to time is given by the gradient of the Hamilton function times xi dot in the i's interval, and this is really given by E transpose E xi dot, and you get the dissipation term, which is the part that is negative semi-definite plus the input and output term. And you can show that the dissipation inequality holds up to an order which is the order of the Runge-Kutta or Gauss-Legendre collocation method. And you can actually show for a quadratic Hamiltonian, so if the h is a quadratic function in this state, and you use Gauss-Legendre collocation, for example, the implicit midpoint rule, then you get the discrete dissipation inequality is exact. So these are good methods. These are the way to do the time discretization. So now we have to look at the Pde setting. For the Pde setting, there are many different approaches. You could do an operator theory approach. You can use a differential geometric approach via gradient flow. This is called generic. Or you could use formal Dirac structures, or you could use structured Pde systems with inputs and outputs. There are many different approaches just in the last few years. It's a very hot topic. But let's look at our two Euler equations. So the first thing, if you want to make it port-Hamiltonian, you also have to deal not only with these three equations that we had before, but you have to also add an equation for the entropy balance. So S here is the entropy. It's an extra equation. And you add this to the system. And if you do that, then it turns out, after you look at it very carefully, you can show that the resulting system is port-Hamiltonian as an operator equation. And then you can go to the weak form. You have to find out what variables you're using. So you use density, momentum, and internal energy. And you write the energy function as a kinetic plus potential energy plus a thermal part. You split it in this way. You introduce a Hamiltonian, which is just the internal energy minus the thermodynamical part. And then you can write down the energy function as an integral. And when you have an integral, you can do partial integration. You can integrate with respect to test functions, psi and phi, and you get, if you choose them in a finite dimensional space, you get a J matrix that's associated with a bilinear form, and you get an R matrix, which is associated with a bilinear form. I'm not going to tell you the details here, but it's straightforward Galerkin type of approach. Then you have to deal with the boundary operators in a clever way. And it turns out you need one more extra condition. This is called the non-interaction condition, that J times the formal derivative of the entropy is 0, and R, the dissipation terms, times the formal derivative of the Hamilton function is equal to 0. And so that flows and the Hamiltonian and the gradient do not overlap. So this was very short on the Pde setting, but I assure you many of this is straightforward. Now we can ask the question, hey, but if we do partial differential equation and we do Galerkin projection, then we have the problem that we have to solve these huge ODEs systems. So I write them in such a way. So that's now an operator equation where the x is in a finite dimensional subspace. And you note here that we don't have the gradient of the Hamiltonian anymore here. This has been incorporated into the E matrix. And so do Galerkin projection. So you put your state variable in a reduced subspace, finite or even very small. And then you multiply with the projection matrix VR transpose from the left, or you do a weak formulation and take a finite dimensional subspace for the test space, which would be then also the same space, so get a Galerkin. And when you do the projection, and this is an normal basis, then the resulting system is again a port-Hamiltonian dA, and all properties are preserved, but you're making an error, and this error can be estimated. I will come to that in a minute. So let me take a system from the gas network, which is even easier. So we don't have the feed-through term, we don't have the P here. It just looks like this. The E matrix is mass matrix for the pressure, mass matrix for the velocities, and then we have the stoichiometric matrix, which does the interconnection. And we have a dissipation matrix, which describes the damping in inside the pipes. And we have an input matrix, B. You find such a projection matrix. I didn't tell you yet how you choose a good basis. That's an art. So you choose it, you split it into 3 parts to the 3 components. By the way, the third component, x1 and x2, is pressure and velocity, and x3 is a Lagrange multiplier for the interconnection points, so the nodes and the Kirchhoff's laws. And so you split your space into 3 parts and your x variables in the same way. And you want an orthogonal projection, but if you split it in a matrix way, then even if VR is orthogonal, the subparts are not orthogonal anymore. So you have to do a little bit of extra computation. You use a so-called cosine sine decomposition for V1 and V2. And if you do that, the cosine sine decomposition is a decomposition where you find a unitary matrix U1 and the unitary matrix U2, and the matrix of cosines and sines on the diagonal. And then actually, in this case, we can even do it with an orthogonal X. And you can do that decomposition. And if you follow your projection with such an extra cosine sine decomposition to orthogonalize, then, for example, here is the pressure V1 with and without this correction. So this blue nervous curve here is coming from the non-orthogonality in your space. So you need to do a little bit extra in this case. And let me show you what comes out. So take a little network here, put a PDE on each of the pipes. This is about 10,000 degrees of freedom. This is the original in blue and the reduced model with degree 2 differential equation, 10,000 to 2, and it looks already pretty good. If you take 5, you cannot really distinguish it anymore, and with 10, it's so close that you cannot believe it. And if you have more damping, it gets even better with a smaller number of modes. So you can really approximate these acoustic waves in the pipes with differential equation of size 2 instead of 10,000. So we're almost there, but what we also want is we want to use this in a clever way and to find a compromise between error tolerance and computational speed. And so in order to do this, we have to do the sensitivities when moving along in the model hierarchy. So what errors are we doing when we go from one node to the next? So we did error estimates for all of these errors that we do when we simplify, and also for time and space discretization. And we use that in simulation and optimization. So here's a little example. So we have a 4-level hierarchy. M0 is the isothermal Euler equations, together with boundary condition and Kirchhoff's laws at the node. M1, we set this term coming from gravity to 0. That's model M1. M2 is model M1 plus setting the quadratic term ddx here rho v squared equal to 0, and M3 is the model M2 and stationary. And then we did sensitivity analysis for all components, and we designed a cost function which we did by tuning to simulation models, a cost function which has a factor here corresponding to the time discretization, a factor to the space discretization, and a constant factor to which model we are using. And then we look at the different model and look at the computational cost, and we tune the model in order so that clearly the model M3, which is the simplest, is much faster than the other models which have a quadratic growth. And if we did this for example, for this test network, and we required that the total error should be less than a tolerance, and the total error is the error in changing the model, the error in changing the space discretization, and the error in changing the time discretization divided by the number of nodes, then we could save a computation time of 80%. And we can also use this in cost optimization. So we designed the cost function for the cost that is used in the compressor station. And so here, eta d is a discretization error, space and time together, and eta m is a modeling error. And then we said, okay, we want 10 to the minus 3 here, so we could adapt the model so that we choose the fitting model so that the error is less than 10 to the minus 3. So in the model, we should take the second level, and in the discretization, we take 1, 2, 3, 4, 5, the fifth level. So these are two different real-world gas networks, and so we could really minimize the compressor cost. And we've also done this for the heat system. So the dashed curve is what the households use in this district heating network. So the aggregated power consumption, and then we played with the models, and we played with discretization so that we are staying below a certain tolerance here, and you can see we can really control the power consumption of the households in an optimal way. Okay, let me conclude. What about our wish list? So we want representations so that coupling of models works. Done. We want a representation that is close to the real physics. Indeed. It should have nice algebraic and geometric analytical properties. I didn't talk about them much, but they are really nice. They should be easy to analyze. Easy, maybe not true, but they can be analyzed, and we have lots of results in this. And at least in the constant coefficient and locally in the nonlinear case, we have normal forms. And we can do model reduction in space and time discretization. And port-Hamiltonian systems are really a great system class. Almost all the wishes are fulfilled. Fantastic. But many things to do. So the real-time control means we have to build these reduced models, and not only for one part, but for every single component. We have to incorporate other domains if we want to couple, for example, to the electric system. That's what we're currently doing. How to bring in stochastics in the model is pretty much an open problem. The stability analysis and how far we are away from an unstable situation. So instability can only come when we bring in extra energy from the outside. Otherwise, it would be stable, but that's what we're doing. Error estimates, and in particular, an open problem is data-based realization of such port-Hamiltonian systems, and we're building software. And with this, I would like to close and thank you for your attention and my sponsors for their support, and my colleagues and friends that work together. The names are in the references. With this, I would like to close. Thank you very much.
Thank you very much, Volker, for the very, very nice talk. Are there any questions?